Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This lecture is a continuation of a series of lectures on exponential and logarithmic functions for a college algebra student. You should have already gone through a review of exponential functions, a review of graphs of exponential functions, logarithmic functions and their graphs, logarithmic properties, and then solving exponential and logarithmic equations. This is kind of the end section typically to exponentials and logarithms. There is a section beyond this sometimes where people have data modeling using data points, but that's not the purview of the course for college algebra at our college, and most colleges don't have that either. So I just end exponentials and logarithms with this topic, and it's a huge topic, a lot of stuff to it, but really it condenses down quite nicely because all exponential and logarithmic functions and models kind of operate the same way. So let's start this by talking about a small topic, or not such a small topic actually, doubling time and half-life. Half-life tends to be very intimidating for students. I recall when I was a student, I was very intimidated by half-life problems. Turns out that they're very, very, very easy to work with once you get used to them. They don't cause a lot of issues. But let's first go to this wiki page and just read through just a small portion of this about Moore's law. Moore's law is the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. So Moore's law is really a statement about how fast technology moves. And his observations have been confirmed from the early 70s up to almost today. It's starting to slow down a little bit, but the reality is that every couple of years, our ability to compute and the swiftness with which we can compute doubles, and that's actually pretty awesome. The power of doubling, as we've seen in our prerequisite videos, is really it's pretty crazy how quickly that grows. Now, if you don't know much about transistors and electronics, I'm not going to tell you that I know about the circuitry very much, because I don't, but I do know that really what you're trying to do is fit more transistors on smaller and smaller chips so that eventually you get these little transistors, these little basically gates, if you will, that allow electricity to kind of move between them and also then allow for computation. You want the distances between those to get smaller and smaller. There's been a barrier for years prior to this point of about 10 nanometers. And Intel still is kind of struggling with that, but AMD I think just reached 7 nanometer technology, which just means that the space between the transistors is that small, so information goes that much faster. And you would not think that that little small distance makes that much of a difference, but when you have a very dense chipset there, or a dense set of transistors, and I hope I'm saying all this correctly, to be honest with you, but when you have that type of density, the smaller space is not just between two little pins, it's actually between thousands of them. And so the faster that the smaller the space, the much faster the information can be computed. So anyhow, so let's look at this problem here. In 1971, the Intel 4004 chip, a breakthrough for its time, had 2,300 transistors. Okay, that's pretty cool. So that seems like a large number, whatever that means, right? Assuming Moore's law is true, predict the number of transistors on that a modern chip should have, and for reference, the Apple A13 or A13 Bionic currently has 8.5 billion transistors. So let's see. We're going to assume Moore's law holds. It's 1971, so year zero will be 1971. And in year zero, 1971, that chipset had 2,300 transistors. Okay. We don't have a second point. You cannot, I just gave you this for reference, but it's not actually a second point. However, our population model for any type of exponential growth, assuming it is exponential growth, looks like this. And because we know it's doubling every 2 years, we know it's going to be exponential growth. Whenever you're doubling, tripling, or taking half of a population, it's exponential growth or exponential decay. The initial population of transistors in 1971 was 2,300. It's doubling per 2 years. Remember, that was early on in our lecture series. I think the lecture video that it was the video on finding equations of exponential functions. So if you look through my video playlist, you can review that topic there. Anyhow, this should be a pretty darn good model for Moore's law. So let's see what the number of transistors should be on a chip today. Well, 1971 was quite some time ago. Let's see. So if we get to 2001, that'd be 30 years. And 2011 would be 40 years. And then 2020, which is now, would be 49 years. So we'll look at P of 49. And I'll say equals for now because we're going to approximate in a moment, but for now I'm just entering in the actual value, 49 halves. And then we can go to a calculator to compute that out. That's one thing about exponential and logarithmic models. You need a calculator. So here we are in Desmos, and I just typed in the function. Now I just want to know what P of 49 is. And you can see that's a huge number. I'm just going to write this down here, 5.457, and we'll just keep it at those 3 extra digits there. The rest is kind of chump change, times 10 to the 10th power. All right, and then we'll go ahead and see what that is. So 5.475, or 457, sorry, times 10 to the 10th. Well, that means that we're going to move that decimal 10 places over. So 5.4, that's 1 decimal place. 2, 3, 4, 5, 6, 7, 8, 9, 10. So 54 billion, 570 million transistors. That's what Moore's law would predict on a chip today. For reference, again, the Apple A13 Bionic chip has 8.5 billion transistors, and that's actually one of the most dense chips out there. So it's a bit of an overshot, which tells us that Moore's law either held for a little while and is slowing down, or really was never doubling every 2 years. Maybe it's every 2.5 years or something like that. And the reality is that a lot of people think that Moore's law is slowing down. So that's kind of the explanation there. Is that we've reached this, not apex in technology, it's just every once in a while when you're going through advancements in technology, you stagnate a little bit until a new player comes to the market to shake things up and to really break through. An example of that is, again, the current situation with Intel versus AMD. Intel spent years trying to break the 10 nanometer technology, and AMD just way passed them up. And continues to break barriers, and Intel still has problems. The part B of this says compute the actual doubling time. And so I should say we have been dealing with what's called a doubling time problem because we want to know how long does it take for a population to double. And initially Moore's law said a population, specifically a population of transistors, will double every 2 years. According to our pace of technology. However, that's not what we're seeing. So let's go ahead and take our actual 2 data points, and that would be the initial data point and the actual data point here. In 2020, the A13 chip having 8.5 billion transistors, and build an exponential model based on those two real pieces of data. And then from that exponential model, figure out what the doubling time it is. How long does it take for those to double? So let's start with the fact that we have the 2 points, and I'll actually write them out. And in reality, the Apple chip came out in 2019. So really, we probably should not have used 49 to compute. We should have used 48. But it actually doesn't, I mean, it makes a difference, don't get me wrong. But it's still going to be off. I would like to look at it though. So rather than looking at 2020, let's just look at 2019. And that is actually not, it's 38 billion. But remember, Apple's chipset in 2019, which is 48 years after 1971, has 8.5 billion. So this is still on the order of maybe 4 times to 5 times greater. So we still have that concern. So those are our two data points we have, 0, 2300 and 48, 8.5 billion. Oh, that's not billion, that's million. Sorry about that. Needed to change that very quickly. All right, so let's go ahead and figure out what our model is. Now remember what we want. We want to find the doubling time. So really what I'd like to have is a population model that looks like this, P0 times 2, because I want to know how long it takes to double. So 2 to the t over n. And the reason why I have that over n is because it's not going to double per 1 year likely. It's going to double per 3 years or per 2.8 years or something like that. And so I need to have that time per so many years in there. And that's, instead of using b to the t, this is as fair, just as fair. In fact, just to let you know, normally you've seen me write this. What I'm doing is I'm saying those p naughts are the same, and actually the powers of t are the same. But I want to know, how can I write b instead of as b? I want to write it as 2 to the 1 over n. Notice in both cases, on the left hand side and the right hand side, there's just one single unknown. So if you knew what b was, it would not be that hard to find n. Along the same lines, if you knew what n was, it would not be that hard to find b. So anyhow, that's how we're going to do this problem. Let me rewrite all this stuff again. We want p0 2 to the t over n. Well, p0 is our initial population, so that's pretty much a gimme. P of t is going to be 2300, because that's our initial population, times 2 to the t over n. And then I get to use my second point to figure out what n is. We're going to plug 48 in for time and 8.5 billion in for the population, p of t. So let's go ahead and set that up. And we now just have a little bit of arithmetic to do. I'm going to divide both sides by 2300. And some people will ask why I choose to not write parentheses on the right hand side here versus writing parentheses on that 2 on the step prior. And the reason why I do that is because if I didn't write parentheses, a lot of people kind of get confused. They might think this is 23,002 raised to the 48 over n. There's a lot of weirdnesses that can happen. So I try to be very explicit with my handwriting to let people know that grouping symbol is on 2, therefore the power is only affecting 2. But once I get that 2300 off of 2 as a coefficient, then I don't need the parentheses anymore. It's very obvious. All right, now I need to unlock this exponent. This exponent right here has an unknown. And the only way you're going to unlock an unknown from an exponent is to use logarithms. So we'll take the logarithm of both sides. You could take the log base 10 or the natural log. I just prefer to use the natural log out of habit. There's no real benefit one way or the other. You get down to this beautiful situation right here. Remember, when you take the natural logarithm of the right-hand side, the power will jump out in front of the logarithm. That's the whole point of taking the logarithm. So you can unlock that power, that exponent. Now I'm going to divide both sides by 48 and the natural log of 2. And then you arrive at this point. And to solve for n, just take the reciprocal of both sides. If two objects are equal, then their reciprocals are equal, as long as neither of those objects is 0. So let's go ahead and take the reciprocal of both sides, and we get that value. Now remember what n represents here. In the original model, this one right here at the top, we're saying we have a population of transistors. We started with 2,300 actually in 1971, and according to Moore, it was doubling per 2 years, but we don't see that pattern actually from the data. So we're going to find out how long does it take to double. It doubles per n years. So n is actually the length of time it takes to double, which is called the doubling time. So all we need to really do now is just grab a calculator. Desmos does perfectly for this. Or I should say Desmos works perfectly for this. Anyhow, so I typed it in there, and it's equal to 48 natural log of 2 over the natural log of that big old number. And we find out the true doubling time, the length of time that it requires for the number of transistors to double, according to the data, is 2.2 years. Very close to Moore's law, actually. So I'm going to write that down. And so now when somebody says, because I listen to podcasts, technology podcasts, people always say Moore's law, blah, 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 every 2 years. You can actually use your education to say, well, according to data, it's actually 2.2 years. Every 2.2 years, the technology doubles. It still is pretty significant. It just takes a little bit longer. The larger the number, the longer it takes to double the population. So that's a doubling time problem, and a real world doubling time problem. Very nicely done doubling time problem, in fact, apropos for what we're going through in technology. Now we're going to switch over to half-life problems, and they have quickly become my favorite style of exponential problem just because they're fun, and they're incredibly applicable to your life. At some point, you will have to take some type of medication, whether it's maybe an bacterial medication, or maybe a birth control medication, whatever it may be. A medication that you take on a regimen for like a week or two or something like that will have a half-life. The reason why you have to take this this dosage of medication, take 2 of these pills a day, whatever, for a week or 2 weeks. The reason why you have to do that is because each pill has a specific, or that medicine has a specific amount of half-life, not even amount, a specific half-life in your body. Your body gets rid of, eliminates drugs from your system through the liver, pretty much. And so, for example, in this one, the half-life of Xanax in a normal human being's body is roughly about 11 hours. So if you took a dose, 11 hours later, only half of that dosage would remain in your body. And so if you take that twice a day, you start building up a certain amount of this drug in your system, because graphically what's happening is this. You had initially, let's say you've never had Xanax, initially you had 0, right? Time 0, really, you've never had Xanax, and all of a sudden you have a 0.5 milligram pill. Okay, so all of a sudden you have this 0.5 milligram pill, and it starts to decay. And actually, the way it starts to decay is kind of a swooping decay. And about 11 hours later, it decays to half of, that's not actually half, it doesn't look like half to me. That might be better. It decays to half of that original quantity in your system. So you took a 0.5 milligram pill. After 11 hours, you only have 1/4 milligram in your body. And then, according to your doctor, twice a day, you take this pill. Well, let's just pretend you just take it every 11 hours, just for giggles. Okay. Then at that point, you'll take another pill and it'll add another 0.5 milligram into your bloodstream. Well, if this is half right here, this is 1 milligram. Right here, you've decayed to a 1/4 milligram in your system. When you take the next 0.5 milligram, all of a sudden you shoot up to having 0.75 milligrams in your system. And again, over the next 11 hours, it will decay to half of 0.75, which is roughly about 30, not roughly, it's exactly 37.5. So it'll decay to that amount. And then you take another pill. And what that's going to do is add another half. So you end up here and it'll decay down, right? And so on and so forth. You can see what happens. You start building up this amount of medication in your system. For certain controlled substances where they really do want you to take it over your life or over maybe several years, they give you a very specific regimen of pills to take. A simple example of this would be birth control. So women who are on birth control, they know they have a specific regimen of which pill to take when. Normally the initial pills are not like that, but as time goes on, the final pills, those are the most important because there's less and less of the chemical in those pills, because you don't want to continually build up in your system this massive amount of dosage of medication. So the next pill that is taken has less of a dose, and the next pill has less of a dose. So you keep at this kind of standard level, just above safety and just below a warning, basically. So that's why long-term medication is to be taken in a specific way, a specific manner. It's like, oh, take these pills for the first 3 weeks, and then in the last week, take this other set of pills in this specific order. Because they kind of lower the dosage in your system and get your body back down to a safe level of chemical in your system. So let's deal with this problem at hand. I've kind of went off on a diatribe there. Sorry about that. The half-life of Xanax is roughly 11 hours. Write a model for the amount of Xanax in a patient after a 0.5 milligram dose. Okay, so let's do that. Population of Xanax in that person's system. They take a 0.5 milligram. That's it. And they tell us it decays to half of its original amount every 11 hours. That's a half-life problem. That quick. That's all you need to do. If it's really very nice. Let me read it again. And actually, maybe I should write below it as I read it. So we initially have a 0.5 milligram dose, which decays by 50%, or in other words, half. You could also say which means you get to keep half. That's both ways of saying that. You decay on a population by half means you keep half a population. But it does that every 11 hours. And that's a great way to read that. Now, I could change this situation to anything I want. Let's suppose that I have a population of ice cream in my house. It's let's say it's a gallon of ice cream in my house. And I say the half-life of a gallon of ice cream in my house is 15 minutes. That means I'll eat through a gallon, not through, but I'll eat half of a gallon every 15 minutes. If I start with 1 gallon, it decays to half of that original amount every 15 minutes. And of course, the next 15 minutes, I eat half of the remaining half because I'm slowing down because I'm getting full. And the next 15 minutes, I eat half of the remaining half of the half of the half. So it's an exponential decay. So again, if you want to graph that, it kind of is cool. You start with 1. After 15 minutes, I'm at half of 1. After 30 minutes, I'm at half of that. After 45 minutes, I'm at half of that. Theoretically, I will never reach the bottom of the ice cream because it's exponential decay, and exponentials never touch the horizontal axis. But while that's unrealistic, it still has some realism for a short period of time. So we built our exponential model for the Xanax in this person's system. And part A says, even though there was a part A before part A, because part AA, I guess, is us building the model. If this patient is only administered this single dose, how much is in their system after 8 hours? And that's all. That is just asking what's the population after 8 hours. So you just ask what P of 8 is. And you plug that in. 1/2 raised to the 8/11. Obviously, you'll need some type of computational technology. In here, I'm using Desmos, and I'm just going to find out what P of 8 is. 0.302. We'll just go to 3 decimal places here. 0.302 milligrams. So that's not too bad. That's just an evaluation problem, honestly. And generally with exponential models, that's how it goes. They want you to build an exponential model, evaluate an exponential model, and then make a prediction about an exponential model. So I could ask, I didn't write it in this problem, but I could ask, when is the population, for example, or the amount of Xanax in this person's system, when is it at 1/10 of a milligram? So when, I'll write that in here. When is, there we go. So all that's asking is, well, when is this output population 0.1? We started with 0.5, we decayed to half per 11 hours. And you can see that this is just an exponential equation. Divide both sides by 0.5 and you'll get 0.2 is equal to 1/2 t over 11, and then take the log of both sides. So I'll just take the natural log here, but you could totally take the log base 10. And you can see that as I do this, I go quickly because there's not really a lot here to talk about. It's just good old arithmetic. So natural log 0.2 divided by natural log of 0.5, rather than half, I just write it as 0.5. And this is approximately equal to 25.5 hours. Essentially, for that amount of Xanax to decay to 1/10 of a milligram in the person's bloodstream, it takes a little over a 24-hour period. So I didn't want to lose that opportunity to showcase other styles of questions you could be asked. There are many other ways to ask this. So if somebody walked in and they didn't tell you how much Xanax a person had initially, but they said, I know the half-life of Xanax is 11 hours, they could ask, when will that amount, how much ever amount it's in this person's system, when will that decay to 10%? And that is a very common question. Notice I tried to highlight the word to, because I'll showcase there's a different style of question that almost is worded exactly the same, but it's not the same. So when will a dose decay to 10% of its original amount? So we don't know what the original amount is, but it was 100% of whatever they gave us. So they gave us 100%. We want it to decay to 10%. And the model otherwise is just 1/2 t over 11, right? We start with 100%. It decays by 1/2 every 11 hours. And we want to know, when is it decayed to 10% of its original amount? And essentially that means you're just solving this equation right here. I'm not going to bother solving this. I'm just showcasing that that's how you would build the equation. You could totally solve that if you want. The other important style and similar style of question is the following. When will a dose decay by 10%? So it's like, think about gas in your gas tank. I want to know when the amount of gas in my gas tank has depleted to 10%. So I don't have a lot left. Versus when will the amount of gas in my gas tank decay by 10%? That means I still have 90% left. So two totally different questions. And in fact, the setup for this one is, if your population started at 100% and it was decaying by half every 11 hours, days, hours, whatever it may be, you want to know not when is it equal to 10%, but when is it equal to 90%, because that's decaying by 10%. You've lost 10%, so you retain 90. So you want to know, when is my population 90% of what it originally was? So that's the difference between those two problems. I don't need to solve either of them, but I'm just saying that's the difference between those two problems. Let's actually finish out the original problem. We did actually a lot of work. The part B here is something that I was just curious about to see if we can even do. This is not something that's normally asked within a textbook, but it is something that you should know in life. Suppose that a patient, or this patient, was prescribed a 0.5 milligram dose 3 times a day. How much Xanax would be in their system after the first 24 hours? So this is actually what we call an arithmetic sum of functions. You have a population of the first dose plus the population of the second dose plus a population function for the third dose, right? And because they're taking them every 8 hours, because they need to take it 3 times a day. So 8 hours times 3 is 24 hours. So every 8 hours, this person's going to take a dose. So let's go ahead and build this up. The first dose, we know it's a 0.5 milligram pill, and it decays in this person's system by half per 11 hours. Now, before we move on to the second function, which will look somewhat similar, I want to note this pill was taken at time 0, and after 24 hours, they should have P sub 1 of 24. In other words, you'd plug in 24 here to find out how much of that initial dose is still in their system. P sub 2, well, this one is going to be a little more challenging. We know that we're going to be plugging in 24, right? I know I want to know how much is in their system after 24 hours, but the first 8, they're not going to use this pill. So there are 2 ways to do this. Probably the easiest way, I think, for most students is to do this. It's the same function, but time 0 is, let's say their first pill was taken is at 8 a.m. So then time 0 for the second function is at 8 hours past that, so 4 p.m. All right, so this is just to get this idea going. And actually, let's make it realistic. Let's say that you have to take this pill 3 times a day. You're not going to take it at 8, 4, and then at midnight or something like that. You don't have that type of time. So let's say you take a pill at 7 a.m. That seems much more realistic. And then maybe 1 in the afternoon. And then again, maybe 1 at 7 p.m. That's good kind of hours to take the pill. They're not really spaced appropriately, but that's okay. They don't need to be. But if that's the case, then we want to know how much is in the system just before you take the pill the next day. So you just want to know how much is a full day of taking these pills, how much of that chemical is in your body after a full day of taking the pills 24 hours later, just before you take your 4th dose. So an easy way to do this is just to say, okay, well, I want in this first case to find out what P of 24 is, because that's how much of this initial dose will be remaining. So I'll just do 24 elevenths there. And then with the second dose, well, if I take that at 1 in the afternoon, then that gives me, 12 plus another 6. So 12 plus 6 is 18 hours of having that pill in my system prior to 7 a.m. the next day. So we'll deal with that as well. And by the way, this is not the only way you could do this problem. I'm just showcasing probably the way that most students will do it. And then finally, the third dose, again, it's the same formula, but the number of hours that you're going to have that pill in your system is less, right? You took it at 7 p.m. and you want to measure how much of that pill's dosage is within your system 12 hours later. So we'll look at P of 12 here. equal to half times half to the 12/11. The sum of these three functions, these three values here, I'll put the little plus between them, is how much of that chemical is still in your system after 24 hours. And I typed it out pretty quick here in Desmos. You could see that right before you take your next 0.5 milligram pill, you still have actually almost 0.5 milligram of Xanax in your system. So you're almost double dosing after a full day. But this is why when you take a regimen of medication, you're building up levels in your system. That's why they say it might take a few days to take effect. It's because what you're doing is you're not inundating your system initially. You're slowly feeding it into your system until you get to this level that it starts to inch to the effective level of effectiveness. Maybe the level of effectiveness for Xanax is 3 milligrams in the system or something like that. It'll eventually inch its way there. It just takes some time to get there, and they want to be careful. So this is the main idea with long, low dosing. So again, this summation is roughly, very roughly, 0.506 milligrams. Now there is a different way to do this problem, but I think it's pretty complex. So I just like it like this for college algebra. If we were in pre-calculus, I'd probably make this a more interesting problem, because what happens in pre-calculus is you start learning sequences and series, and you can do something here with a sequence or a series summation, which is kind of nice, but we won't bother with that here because that's not the purview of this course. Still a very, very cool example using real world mathematics to showcase how much of a chemical's in your system. And you could do this for any drug that's out there that has a half-life. You could just experiment. I'm not saying experiment with drugs. I'm saying you can experiment with the mathematics of the half-life of drugs. And because I love half-life so much, let's do one last example. This looks like a big old example, and it actually is somewhat of a large example, but it's fast. So this again is real world. According to a study published in 2003 by the Journal of Analytic Toxicology, the half-life of caffeine ranges from 2.3 to 12 hours in humans. So if you have a cup of coffee, roughly 2.3 to 12 hours later, half of the caffeine you had is still in your system. Longer half-lives are associated with newborns, which you should never feed caffeine to a newborn, those with liver disease, and pregnant women. Actually, pregnant women, especially in their third trimester, can have half-lives up to 18 hours on caffeine, which means when they have a cup of coffee, half of that caffeine is still in their system by the time they go to bed. In this study, the scientists bought samples of Starbucks 16-ounce breakfast blend coffee each day for 6 days. Fun things that scientists get to do. Contrary to the nutritional information delivered by Starbucks, the samples varied wildly in their caffeine content, from 259.2 milligrams of caffeine on day 3 to 564.4 milligrams of caffeine on the first day. And by the way, I think these were all supposed to have like 260 milligrams of caffeine in them. But you can see, just depends on your barista, you can get a wildly different amount of caffeine in your coffee. So let's make up an example. Suppose a person purchased a 16-ounce breakfast blend containing the 564.4 milligrams of caffeine. That's not unheard of because we've just heard of it. It's actually an experiment. Moreover, for the sake of this example, assume this person initially had no caffeine in their system. So they came in dry, basically. They haven't had caffeine for a few days or weeks. And they quickly finished the coffee at 8 a.m. 5 hours after consuming the coffee, they have their blood caffeine levels tested and find they still have 351 milligrams of caffeine in their bloodstream. Find the half-life of caffeine for this specific person. Remember, the half-life for caffeine ranges from 2.3 to 12 hours. So every single one of us has a slightly different tolerance to caffeine. Most people will claim, I'm super tolerant to caffeine. And you might be, but not everybody is that actually that tolerant. So let's see. Let's go ahead and write out this situation. At time 0, let me use a black ink. I prefer that for my work. At time 0, this person had a 564.4 milligram dose of caffeine. And then, let's see, 5 hours later, right here, so at time 5, they got tested and found that they still have 351 milligrams of caffeine in their system. So at 5 hours, they still have 351 milligrams of caffeine in their system. We want to build a model to find the half-life of the caffeine for the person, for this specific person. That's not going to be too terrible. It's an exponential model. It's just exponential decay because you're decaying by half every hour or whatever it is. So it's going to look like this. The initial population, 564.4, times 1/2, because I want to know what the half-life is. Normally, again, I would write b to the t here, but I don't want to know what b is. I want to know what the half-life is. So I'm going to trade out that b for how long does it take to decay to half? How many hours? In other words, does it decay by half per 2 hours, 3 hours, 4.8 hours, 12 hours? I want to know what that n is. Luckily, we have a second point. At time 5, the output should be 351. So at time 5, our output here is 351. So we're going to be solving this equation to find the half-life. Notice there's only one unknown in this equation now. It's just n. Dividing both sides by 564, we get 351 over 564.4 is equal to a half raised to 5 over n. Notice I also trade out for decimals because you can. That's totally fine. Take the logarithm of both sides. Again, I just use natural log just because I want to. You eventually do this so much that you skip steps as you're going through this because you're just so adept at solving exponential equations. It just becomes like second nature to do stuff like this. I'll divide both sides by 5 times the natural log of 0.5, and then I'll take its reciprocal. So that means that my end result will look like this. And because you guys have had, you're in college algebra, so this is transfer level, you should be able to kind of follow that logic, or pause the video and go ahead and compute for yourself. That's a good way to do it. People who walk you through every little step are not doing you a favor. By the way, I walk you through a lot of little steps, so I often do not do you a favor. But if I was doing you a favor, I would just write the first step, skip 3 or 4 steps, and then get to the end step and just say everything in between you know how to do. But I just hate being that person. But it is true. That's that somebody who does that for you, skips those steps for you, is actually forcing you to think. So I might start including those in my videos, just saying that you know how to do this, so we'll skip these silly little steps. And there you have it. I just hopped over to Desmos here to approximate the value. 7.3 is what I'm going to write that as. So this person has a half-life, or for them, caffeine has a half-life in their system of 7.3 hours. Every 7.3 hours, whatever they had initially decays to half of what it initially was. Now, it may seem like, man, that's only part A. It's going to take forever to solve this problem. Actually, just enjoy the ride. It's a really fun problem to do. The next 2 parts are exactly what I did in the previous example, which I didn't solve. How long before the amount of caffeine in this person's system decays by 10% and then decays to 10%. Decaying by 10% is this situation here. Decaying by 10%, sorry, let me highlight that, means that this person still has 90% of the caffeine in their system. So they just want to know, when do I still have 90% of the caffeine? By the way, this is one of those, I'm going to put part B here. This is one of those that I am going to step through a little bit, just because I want you to see the math here. So I want to have 90% of the original amount left in my system. And I started with my initial population of caffeine. It decays to half per 7.3 hours. N is 7.3 roughly. Ooh, wow, that's interesting. I just don't want to write down 7.3 because I'm going to use the value that Desmos computed, which is 7.296639476 when I do my computation. So I'm just going to use N as a placeholder. You want to know how long it takes for the amount of caffeine in this person's system to decay by 10%, which means they have 90% left. Notice if you divide both sides by 564.4, you're really asking, when is 0.9 equal to 1/2 to the t over n? That is something you need to get used to with exponential problems or exponential models. Is if they say, I need to know when there's 30% left, well, you just solve this equation. You don't care about the initial population because it will actually be on both sides and you'll divide it out. If you want to know when has your population decayed by, let's say, 40%, if it's decayed by 40%, you should still have 60% remaining. So when do you have 60% remaining? If it's decayed by 7%, then you have 93% remaining. If it's decayed to 7%, then you literally only have 7% remaining. In our case, we're decaying by 10%, so we have 90% remaining. Let's go ahead and use logarithms to solve. So this implies the log of 0.9 should equal t over n log of 0.5. And now just multiplying and dividing, we get the following. N log of 0.9 over log of 0.5 should equal t. Notice I'm using n there because I have n saved in Desmos. So I'll just compute over here n times the natural log of 0.9 divided by the natural log of 0.5. And it takes only 1.1 hours for the amount of caffeine in that person's system to decay by 10%. So after 1.1 hours, they still have 90% of the caffeine they originally had in their system. But then you go to part C, and it asks a very similar question. How long before the amount of caffeine in this person's system decays to 10%? Not by, but to 10%. So this is that case where you're asking, well, when is my output 10% of my original? And notice I didn't even bother this time writing the 564.4 because I would have had it on both sides and it would divide it out. So that's kind of nice. And by the way, I can use the previous format here to really solve this problem. N natural log of 0.1 divided by natural log of 0.5 will equal t. It's very fast once you know the patterns. And going over to Desmos here and just changing this 0.9 to a 0.1, you'll get 24.2 hours. That's actually quite a long time, 24.2 hours. So a little over 24 hours for this caffeine to decay to only 10% of its original amount. And then finally, suppose this person suffers from insomnia symptoms. And if they go to bed with more than 80 milligrams of caffeine in their system, they've got issues, right? So maybe they just can't go to sleep if they have more than 80 milligrams of caffeine in their system. So judging based upon this problem that they had at 8 a.m. a 564.4 milligram dose of caffeine, when will it be realistic that this person can actually sleep? So we want to solve in this case. I want to solve 80 equals 564.4 times 0.5 raised to the t over n. In other words, we want to know, given the fact that they've had a 564.4 milligram dose of caffeine, and we know the half-life for this person is n hours, we just have that saved, we want to know when can they go to sleep? When is the amount of caffeine in their system at 80? Because from that point forward, they should be able to go to sleep. So solving this, you would divide both sides by the 564.4. And you would also take the natural log of both sides. And you would get t over n, natural log of 0.5. You would also divide both sides by a natural log of 0.5. And multiply both sides by n. So there you go. This is what I'm saying. Like, I could skip steps. You should be able to follow that without, too much effort. And now I just go to Desmos again. And I do want to reiterate here that you have to use technology when you're doing exponential logarithmic models. It's just how it works. So here we are in Desmos. Our new situation was n times the natural log of 80 divided by 564.4, and then hop outside of that, divide that by the natural log of 0.5. And we get 20.6, roughly 20.6 hours. So let's see. They had this coffee at 8 a.m. And 20 hours later, 20.6 hours later, they'll actually have enough caffeine in their system. It'll have lowered enough so that they can finally go to sleep. Well, that's like 4:30 in the morning, right? 8 a.m., add 20 hours, you're at 4 in the morning, plus another about half an hour. So yeah, roughly around 4:30 a.m. And that's pretty terrible, right? So knowing your caffeine consumption and your tolerance for caffeine is critical, especially as you get older. Just letting you know, it will affect you differently and it'll keep you up way late. We're going to talk about radiocarbon dating. So radiocarbon dating is a process to determine how old a fossil is. Carbon-14, I'm just reading here, is a radioactive isotope of carbon that has a half-life of 5,730 years. It occurs in small quantities in the carbon dioxide in the air we breathe. Most of the carbon on Earth is carbon-12, which has an atomic weight of 12 and is not radioactive. Scientists have determined the ratio of carbon-14 to carbon-12 in the air for the last 60,000 years. Not that they've done that for 60,000 years, but they've determined the ratio from data that allows them to make these predictions over the last 60,000 years. And they do this using tree rings and other organic samples of available dates. Although the ratios change slightly over the centuries, the ratio of carbon-14 to carbon-12, that is. As long as a plant or an animal is alive, the ratio between the two isotopes of carbon in its body is close to the ratio in the atmosphere at that time. When it dies, the carbon-14 in its body decays and is not replaced. So once you start seeing that difference between the ratio of carbon-14 to carbon-12 change from what it normally should be, you know that that creature, that item, whatever it is, died so many years ago. By comparing the ratio of carbon-14 to carbon-12 in the decaying sample to the known ratio in the atmosphere, the date of the plant or animal died can be approximated. And there's a nice little article on it here at this website. Now, let me just tell you that radiocarbon dating it's still used, but it's not the end-all be-all. It's not a panacea. So just to let you know, it is not going to be like the thing. There are basically better methods out there now. So this is not that much of an extension of what we just went through in the previous lecture, because again, previous lecture was half-life, and a lot of students think that the radiocarbon dating problems are different than half-life problems, but they're not. They're actually identical. They're the same problems. I just put this in a different video because, well, I just wanted to. I don't know why. I just did. So here we go. A bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bone? Well, all right, let's first build a model for the amount of carbon-14 in this bone fragment T years after the creature who this belonged to died. Let's see, we don't know how much carbon-14 was originally in the system. So we could say, oh, there's P naught. We just don't know how much carbon-14 was in there originally. But we know that it has a half-life. It decays to half of its original amount per 5,730 years. Double check that because I could be wrong, but no, I'm right. It's the highlighted piece up above. And we want to know, hey, how old is this bone? Because it has 20% of its original carbon-14 remaining. And now we're back to the same stuff we were solving in the previous problems. Divide both sides by P naught and take the logarithm of both sides. Notice again, I'm kind of speeding up my computations. Now you can divide both sides by natural log of 0.5 and multiply by 5730. And you get our value for how old this artifact is. We can go ahead and just plug this into Desmos here, 5730. Let's see, times the natural log of 0.2 divided by the natural log of 0.5. And you get 13,305 because they said to the nearest year. So 13,305 years old. I'm writing that down. So this is a good example of another Half-Life style that's hidden because a lot of people don't think it's Half-Life, but it totally is a Half-Life problem. Again, I don't want to sell you on some fictitious statement that radiocarbon dating is the end-all be-all way of dating items, but the Shroud of Turin was dated that way. The Dead Sea Scrolls were dated that way, but there are better methods now than radiocarbon dating. And radiocarbon dating is only really viable for a short period of, well, I don't want to say short period of time, but it's really only viable from about 62,000 years ago to around 800 years ago. So in that range. There are many samples, though, that are older or younger than that radiocarbon dating doesn't work for. Plus, we have some significant shifts in the ratios of carbon-14 to carbon-12 over the past few years. So that can make it very, very difficult to use radiocarbon dating to approximate age.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.